Hey, this is Mr. A, and I want to talk about projectile motion. But before I do that, I want to talk about motion in general. And we have some equations for motion which are very powerful and useful in solving equations where we're trying to determine or predict the location of an object. So I want to introduce you to the first equation of motion, which looks like this. The location of an object depends on where it started from, how fast it's going, and if it's speeding up and slowing down. So I have written variables for all this information. The distance it's going to be at depends on where it started, d0, the velocity, the speed times the time, plus 1/2 the acceleration times time squared. I've given the example in class, and I'll repeat it here. If you're driving down Interstate 85 South, and you're going to Georgia, and you call me on the phone and you want to know how far it is to the state line, I'm going to ask you, where are you at right now? Maybe what mile marker? How fast are you going? And are you speeding up or slowing down? And given that information, I can tell you when you're going to get to the state line. Today's problem, I'm going to be talking about projectile motion. And projectile motion obeys the same equation of motion, but you have to consider motion in the horizontal direction and motion in the vertical direction. So in the example that we're going to be working, if I'm shooting a cannon off of a cliff, the cannon is going to have some motion in the horizontal direction, and it's going to have some motion in the vertical direction. And if we're looking at vectors, like we have looked at vectors before, you know that there's going to be some resultant. And so the cannonball doesn't go off in the horizontal direction forever and ever and ever. It falls to the ground. There's some speed with which the cannonball leaves the barrel, the muzzle velocity of the cannonball when it leaves the cannon barrel. It has some speed in this direction. And then while it doesn't have any speed in the vertical direction initially, it has the acceleration of gravity. So it will begin to speed up as the cannonball moves out, and it'll move down. So we have to look at this motion equation and break it down for both the x direction and the y direction. I'm going to write dx by putting sub x for d, and I'm just going to try to fill in these variables with what I know about the situation. If we consider that distance 0 is up here at the top of the cliff, or distance 0 in the x direction is here at the bottom of the cliff, then the cannonball is starting out at a location of 0. Now we're going to add to that the speed of the cannonball multiplied times the time. And in our equation today, the speed, the velocity of the cannonball in the x direction is 20 meters per second. So I write 20 t. I'm going to add this third term, which is the acceleration term, which would be the acceleration in the x direction. But there is no acceleration in the x direction, because once the cannonball leaves the barrel, there's no rocket motor on the bullet. Whatever velocity that it had when it left the barrel That's the velocity it has as it moves forward in time. So there's no acceleration term. So dx simply becomes 20t. Let's check and make sure that the units are working out right. This is 20 meters per second times time in seconds. The seconds cancel, and it's going to leave us with a distance in meters. Okay? So whatever the time is, we plug that time in, and then we get a distance. Now, when we're trying to find dy, we need to break this general equation down again. So dy is equal to, where does it start at? It starts at 0. dy starts at 0. And then we add the initial speed. Well, if you're holding a ball, initially, before you drop it, its initial speed is 0. Okay? And now for our third term, our acceleration term, we actually do have some acceleration. And that is the acceleration of gravity. So in this case, I would write 1/2 at squared. But now a is really the acceleration of gravity. And acceleration of gravity, we can either use 9.8 meters per second squared, but for this activity, I'd like for you just to use 10 meters per second squared. So this equation becomes, we don't have to write the 0 terms, dy simply becomes 1/2 10t squared. Okay? Or, simplified even more, 5t squared. All right? So now you have equations for the distance out from the cliff the ball goes as a function of time, and you have an equation for the distance the ball drops as a function of time. And you'll use these two equations to complete the data table on the worksheet and to fill in the profile of the projectile on the graph.